Hello everyone and welcome back. Today we'll be starting off with our chapter 2, that is Introduction to Computer Vision. So in the previous chapters we were introduced to basics of machine learning and how machine learning works, what kind of basic programming goes into designing a basic neural network, and we knew the labels, we knew the inputs, and finally we got or inferred our outputs. So, a logical next step is to apply these concepts to computer vision, where we will have a model learn how to recognize content in pictures so it can see what's in them. So, basically, we are here to make a model see how a computer or how a machine can see what we actually can see in a picture or in a photograph. In this chapter, you'll work with popular dataset of clothing items and build a model that can differentiate between them, and thus seeing the difference between different types of clothes. So, we'll be recognizing the clothing items with help of machine learning. So here are some examples of clothing, like you can see a coat, you can see a shirt with a tie, you can see trousers, you can see heels, you can see normal sneakers, a beautiful blue dress, a purse. So there are a number of different clothing items here, and of course we as human beings can recognize them and we know what a shirt looks like or what a sneaker looks like, but the machine does not. So we'll be learning about how we can teach a machine that what is what. How could you explain this to somebody who has never seen clothing? So that's the basic question. So if you meet someone who has never seen clothing, how would you describe a shirt to them? So consider how you learned to recognize all these items. So how we know that this is a shirt and this is a trouser, right? Because we have seen lots of different examples and we have gained the experience over the years of how these things look like. So whenever we look at an apple and an orange, we know the difference. So here we'll be using Fashion MNIST dataset that contains many images of clothing that we'll be using as our input images. Then the Fashion MNIST dataset is kind of a sister of the MNIST dataset. So the MNIST dataset has around 70,000 images of handwritten digits from 0 to 9, and these images are grayscale of 28 by 28. The Fashion MNIST is designed to be a drop-in replacement for MNIST, and it has just 10 different types of clothing. So it has many images, but it has the labels are just 10. So there will be different images of 10 labels only from 0 to 9. So here you can see Fashion MNIST dataset. There are many images, but there are just 10 labels or 10 classes. It is very nice variety of clothing, including shirts, trousers, dresses, and lots of shoes. And you may notice it's monochrome. So each picture consists of a certain number of pixels. So each image has certain number of pixels that varies from 0 to 255 because it's monochrome. This makes the dataset simpler to manage because the machine captures image in form of pixels. It does not understand a complete picture. It understands pixels. So here is one of the image from the data set. It's a rectangular grid of pixels, and in this case the grid size is 28 by 28. So it's a rectangular image of 28 by 28 pixels. Each pixel is simply of the value from 0 to 255. So let's take how you can use this pixel values with functions you saw previously. So how we'll be using these images to train our model. Like in first chapter we did that we found the answer for x value. If the value of x is 10, what value we'll get for y. So simply we'll work out in this also. Neurons for vision. So in chapter 1, like I was saying before, so we found that there was a relationship that y is 2x minus 1. But here we have images, we don't have x and y's. Each of our images is a set of 784 values. So earlier, as we saw, that we had an image of this shoe, and it was a grid size of 28 cross 28. That makes up of 784 values between 0 to 255. So 0 and 255 depends upon the kind of grayscale. So what is the value? Is it white, or is it black, or it reaching black, or is it grayish? So 0 to 255 varies with that. They can be our x. So values of the pixel values of the image will be our x, and we have 10 different images. So there are 10 classes. So y would be 10. That we have 10 different classes or 10 labels. So now we have x and we have y. We just need a function. So here we have a single neuron, and we provide the x, we give it the weights and the bias, that is m and c, to learn, and finally we get the relationship in form of y. But given that we have 784 x values per image and y is going to be 0 to 9, so it is clear that the function won't be y is mx plus c. It does not fit the relationship of y is mx plus c, because for y the values can be 0 to 9, but for x the values are 784. So it cannot satisfy the equation. But what we can do here is, if we put number of neurons together and they're working together, so single neuron won't be working here, but if we use number of neurons together so that they learn the parameters together and finally combine it in combined function of all these parameters working together. So we'll get a combined result. We'll get one result but combined from all those. We can see if we can match that pattern to the desired answer. So as you can see here, these on the top you see the blocks. These are the pixels of image, and we are giving it to the number of neurons. All the values are being fed to the number of neurons in a fully connected layers, and then we are combining all the outcomes of these all neurons, and we'll get the answer, that is a boot. Now consider each neuron's weight and bias to be randomly initialized. Because random initialization is there because we actually don't know the value, we're just guessing. Then we sum up the values of the output of each neuron. We are going to get a value. This will be done for every neuron in the output layer. So neuron 0 will contain the value of probability that the pixels add up to label 0. Neuron 1 for label 1, and etc. So over the time, we want to match that value to desired output, which for this image can see is number 9. That is the ankle boot that we will see in the next here. So in other words, this neuron should have the largest value of all of the output neurons. So whichever the label is true, it will carry, the neuron will carry the largest value related to that particular label. So if the outcome comes to be 0, that means it corresponds to the label 0, and that is our answer. That is the specific image that the computer is seeing right now. Given that there are 10 labels, a random initialization should get the right answer about 10% of the time, because there are 10 labels. So here the loss function and optimizer comes into play, so that epoch by epoch this 10% is increased and we get better answers. So over time the computer will learn to see what makes a shoe, or a dress a dress. Then we will be continuing with designing the neural networks. So first we'll be going through all this written part of the chapter, and then we'll be jumping to the code part in the collab. Now let's move forward and take a look at how we'll design a neural network for fashion MNIST dataset. So it's kind of similar thing that previously we used for model. We used Keras API. So here is the same thing, that model equals keras.sequential, and then we have 3 layers. First is flatten, second is dense, Third is also dense, but each of the dense layer have different number of neurons. So first one has 128 neurons, the second one has 10 neurons, and with different activation functions. We learn about these more as we progress. So the first flatten isn't a layer of neurons. So as you can see here already that we haven't specified any number before input shape. We just have input shape of 28 cross 28, but we haven't mentioned any number of neurons because it isn't a layer of neurons but it's a input layer specification. So we are telling the machine that a model will have the input of 28 cross 28 images, and instead we just wanted to treat it like a numeric values, because of course we know that machine won't be easily understanding a image unless and until it's converted in form of numbers, right? The flatten takes that square value, a 2D array, and turns it into 1D array. So flatten means to convert a 2D array into 1D array so that it can be easily fed to the model. The next one is the dense layer, which has 128 neurons, and as you can see that it is the middle layer. So first you have a flattened layer, then you have a dense layer, then again you have a dense layer. So the second one layer is the hidden layer or the middle layer. It's called hidden layer because as a caller you cannot see the middle layer. It is a layer between the input layer and the output layer. So if you're thinking why we use 128 neurons, so it's simply arbitrary value because there is no fixed rule for number of neurons to use. It comes to you as you practice. So more neurons means that it will run more slowly. The model will train more slowly because it will have more number of neurons, so more number of parameters it has to learn. So the more number of neurons could also lead to a network that is great at recognizing training data but not so good at recognizing data that hasn't previously seen. So this is called overfitting. In easy language, if you have provided all the data to the system and the machine has memorized all the data, so of course when you give it some of the values from the same data it has memorized, it will give you the correct answer, right? But when you provide some question that is out of the box that it hasn't seen before, it will not be able to answer correctly or perfectly. So this is called overfitting, when the model has memorized the training data because the number of neurons are so many that it took time to train, but it has memorized everything. And similarly, if you have few neurons, means that the model might not have sufficient parameters to learn. So if you have less neurons, so the model might not be able to guess right or memorize it, but it has more neurons, then it will definitely memorize all the values. That also we don't want. So there is a kind of trade-off between the two. It takes some experimentation over the time to pick the right values, and the process is typically called hyperparameter tuning. Hyperparameter is a value that is used to control the training as opposed to the internal values of neurons that get trained or learned, which are referred to as parameters. So hyperparameter is just a value that is used to control the training as opposed to the internal values of the neuron. You might notice that there is also an activation function specified. So let's talk about the activation function now. So the activation function is a code that will execute on each neuron in the layer. So it is a code that is executed on each neuron in the layer because we have specified. So if we have 128 neurons, all 128 neurons will have an activation function. TensorFlow supports a number of them, but a very common one in the middle layer is ReLU. So ReLU stands for Rectified Linear Unit. It is a simple function that returns a value if it is greater than 0. So what's the function of ReLU? That it's a simple function that just returns a value if it's greater than 0. In this case, we don't want negative values being passed to the next layer to potentially impact the summing function. So instead of writing a lot of if then code, we simply activate the layer. So its ReLU is just like a if then code. So if we say if the value is less than 0, just don't return anything, because at the end of this activation function there is a summing function. Now think that you have equal numbers of plus or positive values from the activation function, and you have equal number of negative values from the activation function. Now before the activation function, now what happens if you apply all these values to a summing function before the activation function? Say there is no activation function, you have equal number of pluses and you have equal number of minuses, and you provide these all to a summing function. What will happen? The net value will be 0, and we don't want that. We want an answer. So in fact, we have a if then case here. Rather than writing code for if then else, there is a simple ReLU function that we can use that does not allow negative values to pass to the next layer. Finally, the last dense layer has 10 neurons because we had 0 to 9 labels. We have 10 classes, so we want 10 neurons at the output stage. Each of these neurons will end up with a probability that the input pixels match that class, so our job is to determine which one has highest value. So at the end of all these 10 neurons, we'll have probabilities. So we'll need to find out which one has the highest probability, and that's our answer. That's simple. So loop through them to pick that value, but the softmax activation function does that for us. So what does the softmax activation function do for us? So each of these neurons will end up with a probability that the next pixels match that class. So our job is to determine which of the highest value. So we have to find the highest value of probability. We could loop through them to pick that value, or we could just use a softmax function. We are just using softmax function to find the value of highest value here at the output. So now we train our neural network, and the goal is that we can feed 28 cross 28 pixel array, and the neurons in the middle layer will have weights and biases. Then when combined will match those pixels to one of the 10 output values. So here's the complete code. So firstly we import TensorFlow as TF. Then we get the data as tf.keras.datasets. So data keras do provide you a lot of datasets that are inbuilt, and you can just call them like this. So we've called datasets.fashionMNIST. Finally, we divide the data into training images, training labels, test images, and test labels. So when we are training the model, we'll be using training images, and when we are testing the model, we'll be using the test images and test labels. So training images, we divided by 255.0 because we really want to normalize these images into from 2D array into 1D array, and similar for the test images. So we want the pixel values rather than 255.0. Model is equals to tf.keras. This we have already seen and we have gone through. So we'll jump to model.compile. We'll use Adam optimizer. We'll use sparse categorical cross entropy for loss, and we'll measure the metrics of accuracy. So then we fit the model with training images and training labels with just 5 epochs. Now let's take a walk through each of these lines of code that we have written one by one. Moving on to datasets that we got from Keras. So it's written that Keras has a number of built-in datasets that you can access with a single line of code like this. That's what's given earlier. So data equals tf.keras.datasets.fashionMNIST. So in case you don't have to handle downloading 70,000 images, splitting them into training and test sets, and so on, all it takes is a single line of code. So you can also use or check out TensorFlow datasets where you will get access to a lot of datasets that you can use in your future projects. Then we divided the dataset into training images, training labels, test images, and test labels using load data method to return our training and test sets like this. So Fashion MNIST design is designed to have 60,000 training images and 10,000 test images. So we have total of 60,000 training images and 10,000 of test images. So the return from data.load data will give you an array of 60,000 28 cross 28 pixels array called the training images and an array of 60,000 values 0 to 9 called the training labels. Similarly, for the test images, we will have 10,000 28 cross 28 pixel array of that test images, and labels will have 10,000 values from 0 to 9. So our job is to fit the training images to the training labels in manner like we fitted Y to X, right? Now we'll hold back the test images and the test labels because we do not want a network to learn or memorize the test images or even see before it has been trained. So the model will be trained on only training images and training labels and not on test images or test labels. So as the name suggests, test means we'll be testing using that images and labels for testing purposes. So the next line of code is training images by 255.0 and test images equals test images by 255.0. So Python allows you to do an operation across the entire array. So as we have told earlier that we'll have test or training images of 60,000 28 cross 28 pixel arrays and 10,000 28 cross 28 pixels of test arrays, right? So both are arrays. So Python allows you to perform a division operation. So divide both the images of training images and test images by 255.0. Recall that all of the pixels in our image are grayscale, so the value lies between 0 to 255. Now, what we have done here is dividing by 255 is normalization. But why do we want to normalize? Right, the question arises for why. Dividing 255 thus ensures that every pixel is represented by a number between 0 to 1. Right, this process is called normalizing the image. So as we know that our machine only understands zeros and ones. So we normalize the image into zeros and ones so that we have the lesser gap rather than going from 0 to 255. The math for why normalized data is better for training neural networks is beyond the scope of this book. But bear in mind, when training a neural network in TensorFlow, that normalization will help you improve the performance. Often your network will not learn and will have massive errors when dealing with non-normalized data. That is, the y is equals to 2x minus 1 example from chapter 1 didn't require the data to be normalized because it is very simple, right? The data was so simple and so less data that we never felt the need of normalizing it. But in case of images where the data ranges from 0 to 255, we have to normalize it so that it will help us improve the performance. Next, we define the neural network that makes up our model as discussed earlier. So this is the neural network that we've already discussed about the 3 layers. Then we compile a model using model.compile. We have the optimizer that is called the sparse categorical cross entropy, and it's one of the arsenal of loss functions that are built into TensorFlow. Well, what he says is that again choosing which loss function to use is an art in itself, and over the time you'll learn which ones are the best for which scenario. The major difference between this model and the one we created in chapter 1 is that instead of us trying to predict a single number, here we are picking a category. So earlier we were like giving for a value of x, we were predicting the value of y, but now we are giving an image and we are asking which category does it belong to. Sparse categorical cross entropy is a good choice for categorical loss function and to categorize the item in from 0 to 9. The same applies to choosing an optimizer. The Adam optimizer is an evolution of stochastic gradient descent optimizer we used in chapter 1. So it has been shown to be faster and more efficient. As we're handling 60,000 training images, any performance improvement we can get will be helpful. You might notice that a new line specifying the metric we want to report is also present in this code. Here, we want to report back on accuracy of the network that we are training. So remember in the code there was written metrics in commas, there was written accuracy. So we want to report back the accuracy of the network while we are training it. Now, in this case, it's more useful to us to see how the network is learning by looking at the accuracy, where we will return how often it correctly matched the input pixel to the output label. So accuracy is nothing but a match between if the machine matched correctly between the input and the output label. Next, we are fitting the model using model.fit. So we'll be providing training images, training labels, and just 5 epochs. So finally, we can do something new. Evaluate the model using a single line of code. We have a set of 10,000 images and labels for testing, and we can pass them to the trained model to have it predict what it thinks each image is compared to the actual label, and sum up the results with model.evaluate. So when the model is trained finally, as we've seen in chapter 1, we have these many epochs. We have 60,000 images, training images, and once the model is trained, we'll show the loss, that is 0.2940, and the accuracy means the model thinks that it has matched from the inputs to the output labels to about 89% in just 5 epochs. So it's a very big accuracy for just 5 epochs. Next is, if the data is now just the training data, but what on the test data? We have actually provided the labels and the training images to the machine, but now we want to test if it can actually predict something or it has just memorized it or overfitted. So if we look at the results, it gives us accuracy of 87%. That means in this case, accuracy of model was 87.36%, which is not bad considering we had only 5 epochs. Probably if you're wondering if the accuracy is so lower for test data than for the training data, so it is very commonly seen. Then when you think about it, it actually makes sense. The neural network only really knows how to match the input it has been trained on to the output of those values. Our hope is that given enough data, it will be able to generalize from the examples it has seen, learning what a shoe or dress looks like. So it is able to generalize from the examples, but hope that given enough data, it will be able to generalize. But there will always be samples of the item it hasn't seen before. So that's why the accuracy drops there. For example, if you grew up only ever seeing sneakers, and that's what a shoe looks like to you, when you first see a high heel, you might be a little confused. From your experience, it's probably a shoe, but you don't know for sure. So that's a similar kind of concept. So the machine might get confused seeing a different kind of example if for a shoe. So as it said that if you have seen sneakers everywhere all the time, you might not be able to say that if a high heel is exactly like a shoe or not. So exploring the model output, what the output looks like is, we have a good gauge of its accuracy using the test set. So let's explore it a little. So we needed output and we want our model to predict something. So we give it a test image for model.predict, and then we write down the classifications, what kind of classification or category it chooses. So we'll see here is that we'll get a set of classification by passing the test image to the model.predict. Then we'll see what we get if we print out the first classifications and compare it to the test label. So it gives us, here you can see 9. So that's the predicted label because that label started from 0 to 9. You'll notice that the classification gives us back an array of values. So this is an array of values here, and these are the values of 10 output neurons. These are the values of 10 output neurons. The label is actually label for the item of clothing, in this case 9. So as we take a look through the array, you will see that some of the values are very small. So if we look at, we'll see E05, that is 10 to the power minus 5, 10 to the power minus 7, 10 to the power minus 7, 10 to the power minus 2. But for only few, we'll see that for only one value, we'll see that it is not the really smallest value. So take a look through the array, you will see that some of the values are very small, and the last one is largest by far. It's why largest by far? So because it's 10 to the power minus 1. For rest of these, we can see the values are 10 to the power minus 5, minus 2, then minus 5, then minus 2, minus 7, minus 8, minus 7, minus 7, minus 5. So 10 to the power minus 1 is far more less than far more larger value than 10 to the power minus 5, minus 7 or minus 8. These are probabilities that the image matches the label at that particular index. So whichever index that label matches, that will have the largest value, as we have discussed earlier. So what neural network is reporting is that there is 91.4% of chance that item of the clothing at index 0 is label 9. So we know that it's label 9, so it got it right? Let's try a different value, and we'll be trying a different value for our code while we go to the code. But before that, training for longer and discovering overfitting. So as we have discussed earlier, the more the number of neurons, there is a probability that our machine will memorize the training data, and of course it will lead to overfitting. So in this case, we trained only for 5 epochs, and that is, we went through the entire training loop of having neurons randomly initialized, checked against their labels, having that performance measured by loss function, and then updated by the optimizer 5 times. So we got a round accuracy of 89%. Now what if we change the number of epochs to 50 instead? So here you can see that we got an accuracy of 96.27%. There's a drastic change from 5 epochs to 50 epochs, and the accuracy has changed. Now, if we check for test dataset, the accuracy has also increased to 88%. So there's a big improvement by just changing the number of epochs. We might suggest that training a network for much longer would lead to much better results. So as we can see that if we increase the number of epochs, means we have trained the network for much longer time. So it might lead to better results, as we have seen. But that's not the case always. The network is doing much better with training data, but not necessarily a better model. In fact, the divergence of accuracy in the accuracy numbers show that it has become over specialized to training data, a process often called as overfitting. As you build more neural networks, this is something to watch out for. In each case, so far we have hard coded the number of epochs, so what we were training for. So what if that once we reach a desired accuracy, instead of continuing, we just stop there. We stop the training over there. So for example, if we want to train a model till 95% of accuracy on training set, Without knowing how many epochs that it will take, we could just say use a callback. So what the callback here is, the easiest approach is to use a callback on training. So let's look at the updated code here. So all the code remains same, just we need to add this much of new code, this callback function class that we'll have to use. So what is in this callback class is that we define a function on epoch end which takes in epochs and the log from the training. Then it prints reach 95% accuracy, so cancelling training when the accuracy becomes greater than 95%. So when it gets the log that the accuracy has now reached 95% or above, 95% and above, the it prints reach 95% accuracy, so it cancels the training using model.stop training equals true. So it calls this function and it stops the training over there only. So as we can see, the rest of the code remains the same, and in the model.fit along with epochs we just add callbacks is equals to callbacks, that we are using that class, we'll calling that class, right? This takes in tf.keras.callback.callbacks as a parameter. In it we define on epochs function that we have already discussed, that gives us the details about the logs for each epoch. In these logs is an accuracy value. So all you have to do is, if the accuracy value is greater than 0.95, that is 95%, we just say that stop the training. So we call self.model.stop training equals true. Once we have specified this, we create a callback object to be an instance of the my callback function. Now check out the model.fit statement. You will see that I've updated it to train for 50 epoch and then added a callback parameter to this. When training at the end of every epoch, the callback function will be called, so that at the end of each epoch you will check, and after that about 34 epochs you will see that training will end because the training has hit an accuracy of 95%. So after each epoch we'll be calling the callback class and we'll be checking around and around that if the accuracy has reached 95% has reached greater than 95% or not. So here's the accuracy. So you can see once the accuracy reaches 95%, so it says reach 95% accuracy, so cancelling the training. The summary is, in chapter 1, you learned about how machine learning is based on fitting features to labels through sophisticated pattern matching with a neural network. In this chapter, you took that to the next level. So we took that to next level from just numbers, we went to images. Beyond single neural network, we learned how to create a first very basic computer vision neural network. It was somewhat limited because of the data. All the images were 28 cross 28 grayscale with the item of clothing centered in the frame. So this all matters a lot, that what is the size of the images, were they grayscale or RGB, or whether the images were centered or there was some kind of clutter around them or some other thing was placed along with the main object. So it all has to be taken care of, but it was a starting computer vision project, so we just took it very lightly and basic. It's a good start, but it is very controlled scenario. To do better at vision, we might need the computer to learn features of an image instead of merely the raw pixel. So we want a computer to learn features of an image rather than just raw pixels that were given in this data set. So we can do that with the process called convolutionals or convolutional neural networks that we'll be learning next in the next chapter. Meanwhile, we'll head on to coding session and we'll write down all the code of this chapter 2 and we'll try to run it the fashion-aminist neural network and train our neural network. Now it's time for some coding part, and here I've already written all the code for chapter 2 and just running it and going through it just quickly, because we have already gone through it line by line in the book itself. And all this code will be available on our GitHub, and I'll be sharing the link to the GitHub in the description. So if you haven't checked out it yet, so do check it out. So let's start. First, we have the imports. So we'll be importing TensorFlow as TF, we'll be needing NumPy, we'll be importing sequential and dense. So we'll do it one by one. So first step is imports. Of course, we'll not be able to continue ahead because we won't have imports, right? So first thing first, we need the imports. So we have all our imports in place. We've imported all the things and the frameworks and the tools that we'll be needing ahead. Then we'll come back to callbacks, but first we'll go to data. So after we have the imports, the second most important thing is that we need data. Of course, we are training a machine, but the machine needs to be trained on a data, right? So we'll get our data first. We have tf.keras.datasets.fashionMNIST. So we have our data. Then we'll split our data into training images, test images, training labels, and test labels using data.loadData. We are just simply loading the data. Then we are normalizing the images because it's a part of data normalization, as we have seen in the chapter. So all our data is ready and pre-processed. Now it can be easily used as an input. The third step here is that we define a model, right? Now we have the data, we have the input, we need a model. So for model, we are defining that we have a sequential model which has 3 layers. First is a flattened layer, second is a dense layer, and third is also a dense layer, but both dense layers have different activations. So here comes a model. Then fourth step, it's to compile our model. Well, when the model is defined properly, it's time to just compile it. So we use a Adam optimizer. For loss, we're using sparse categorical cross entropy, and for metrics, we are using accuracy. So next we come to fit. Our model is compiled. Now it's time to fit our model to training images and training labels with epochs 50 and callbacks. Since we have callback here, let's roll up to our callback class. So here is our callback class. So I've already written that callback stops training at a particular accuracy percentage to avoid overfitting. So here we have our callback class, and it has a function called onEpochEnd, which has input of epoch and logs, and checks for accuracy. If accuracy goes beyond 0.95, that is 95%, it prints reach 95% accuracy, so cancelling training. And finally uses model.stop training equals true to stop the training. Here then we use evaluate, that is the sixth part, that is use model.evaluate, because we will be finally evaluating how our model has learned, how much it has trained itself on the test images and the test labels. So let's just evaluate this, and I'll be running. So if you can see, the epochs are running in the back end. Here you see, and once the accuracy has reached 0.95, it says reach 95% accuracy, so we'll cancel the training. So I ran it for around 50 epochs, but it has already been run before, so it's running again. Now I'm running this code, and here you can see first it downloads the data from Google APIs, that is TensorFlow datasets. So we are downloading the test data, training images, training labels. We are downloading all this data, and then the epochs are running in backend. So 1 of 50, we have accuracy of about 82%. Then we see the accuracy goes on increasing from 82 to 86 to 87, 90, 91, 92, and the epochs are still running to its 17th epoch right now. Here goes the 18th, and we'll just wait for a few moments and just come back when it has reached to a certain point when the accuracy hits 95 and above. Now that our epochs have done and our epoch reached just 35, when we attained the accuracy of 94%. But when we reached 35 of the 50th epoch, we got the accuracy of 95%, 0.12, that is more than 95%, and hence our training was cancelled there. Then we got the accuracy for the test data, that was 89% last, and here you can see that we'll be testing for the model output. So let's run this. So model predicted on the test image that it hasn't seen before that it is number 9, because the ninth one got the highest, the largest probability, that was just 10 to the power minus 1. The rest one was 10 to the power minus 12, minus 15, minus 5, even minus 17, and just 10 to the power minus 1 was the one that was the largest of all. Hence it was our label. So here I've used Matplotlib. It's a library that you can use for showing your images. So when I run this, so it gives me a test image output for ninth label. So as we've seen before that the model predicted that the classification for 0th image was label 9, and we can say that for label 9 it was a sneaker. So our model justified that for ninth label and the 0th position there was an image of a sneaker, and it correctly signified that. Now we have written all the code here, and you can just have a look and write it yourself in Google Colab or any other tool that you want to use for writing your code, and just give it a go because it's very simple to write, and use this code for your reference. So I'll see you in the next chapter. Thank you, and do check out the GitHub for the code. Thank you.